Alright, this is more like a review about domain. Now remember that domain is going to be the values of x that you can plug into a function, right? So if you have any function f of x, alright, the domain is going to be, we want to know what you can plug into x, alright, to a certain function. There are certain functions where you might not be able to plug in like all real numbers into a domain, okay? But let's start with the easy ones. Let's start with ones that you can plug in every number. So the first one we have is if f of x equals a polynomial. Okay, so polynomial, alright, or even a monomial or binomial, any of those. So polynomial is something that has, more than one term. Like you can have like x cubed plus x squared minus x plus 1, But you can plug in any number for x, negative or positive, and you'll still get an answer. There's no undefined answers. So we see that it's from negative infinity to infinity, okay? That means that all negative values and all positive values. So it's really another way to say it's like all real numbers. Sometimes they do that, but a lot of times they do this kind of ordered pair kind of thing, negative infinity to infinity. Well, okay. Well, what else would constitute for a continuous function everywhere? Well, you could have functions such as trig functions, okay? Trig functions. And trig functions, right? Not all of them, but most of them are. Like, not most of them, but there are some, like a sine function, that's continuous. A cosine function is continuous. However, a tangent function wouldn't be, because what is the definition of a tangent function? Well, a tangent function is really going to be sine over what? Cosine, right? Now the thing is, this is a fraction, so there's naturally a discontinuity because it's a fraction, or a rational function, right? So anytime you have like a rational function, which is like a fraction, right, you're gonna always have some kind of discontinuity somewhere. Alright, so this is not a continuous function. Alright, what other examples can we have of continuous functions? Well, what if we had a exponential function such as 3 to the power x? Okay? Can you plug in any value for x? Positives. So let's see what happens when you add a positive number, okay? So let's say f of x equals 3x. Let's find 3 of 3. That's going to be 3 times 3 times 3, which is 27. Alright, and then you can plug in really any positive number, and then you can actually get some kind of value. Now let's see what happens if you plug in negative numbers. Say negative 2. Right? Well, we know that from property exponents that anytime you have a negative power, that's going to convert that to 1 over 3 squared, right? So what happens as you go to negative infinity? Right? The denominator gets bigger and bigger and bigger, right? So if the denominator gets bigger and the numerator stays the same, that means the number is actually getting smaller and smaller and smaller, eventually going to 0. But the thing is, it never reaches 0, okay? But it's going to 0 when you go to negative infinity. But we're talking about domains, so technically we could still plug in any number into x and get a value. Alright, so this is also a continuous function. Okay, next, in the next video we're going to move on to discontinuous functions. Alright, let's talk about discontinuous functions, okay? So we know that continuous functions are polynomials, certain trig functions, and there's maybe a couple of others that are continuous functions, but let's look here. What's a very common discontinuous function is what we call a rational function, okay? Rational function is merely a function that is in a form of a fraction, like 1 over x, okay? Now, we know that in math, a fraction, alright, the denominator cannot be a certain number. What can it not be? So in math, we cannot divide a number by 0, right? That's not possible. So the other question is, what are there any other discontinuous points? Well, let's see. If we go to any positive numbers, 1 to infinity, we can plug in that and it'd still be a number. And we can plug in negative numbers for that and it would still be fine. So the way we would write this domain would be from negative infinity, right, to that discontinuous point, which is 0. And then we put a union sign, U, and from 0 to infinity, or shorthand we just say x cannot equal 0, right? But this would be the more formal way of writing it. What if we had like something, a rational function like 1 over x minus 1 squared? Well, in the bottom we have this binomial, don't we? So we're going to have to expand this out and see where x cannot equal to. So x minus 1 squared is going to be 1 over, sorry, it's kind of crammed in here, but you'll get the idea. 1 over x minus 1, 1, and x plus 1. X minus 1, x plus 1, right? So x cannot equal 1 and negative 1, right? Because then that would make these 0. So the domain is going to be from negative infinity, alright, to negative 1, okay, because it can't be negative 1, union, negative 1, oops, that's actually negative 1, comma, okay, to 1, okay, negative 1 to 1, union, and then from 1 to infinity. Because we can have an interval between negative infinity to 1, right? Because we're going from negative to that discontinuous point right there. Right? So we have an asymptote there. Then we have a little interval between the asymptote here to the asymptote at 1, right? So negative 1 to 1. There should be some points that you can plot still. Alright? And at 1 we have another asymptote, so we draw the asymptote. Where we can have any values from 1 to infinity, not including 1, okay? So you got to make sure that everything here, alright, you put in parentheses. Alright, let's look at a log function, or natural log function, okay? These are inverses of exponential functions, right? Like e to the x, or like 10 to the x, right? Log base 10. So when we looked at log functions, when it came to the domain, they were actually what? They were continuous. You can plug in any number for x. But because of the property of inverses, right? Right, when we look at what was it, exponential functions? Alright, when it comes to the range, so the value of y's, it's not going to be all values of y's, right? Because we know it's going to be from 0, not including 0 because there's an asymptote there, to infinity. But we know that in inverse function, what happens is that the original function, the domain, becomes the range of the inverse function, and then the range of the original function becomes the domain. Now, remember, these exponential functions, they don't have a what do you call it, a continuous range, so that means that the domain of these log and natural log functions are not going to have continuous domains, okay? So if you look at the graph of a natural log or whatever, right, as you go to 0, it's going to go to negative infinity. Then as you keep going to infinity, it's going to go to infinity, right, gradually. So the way we would say the domain of this function works is going to be from 0, right, not including 0, but it's getting close to 0, to infinity. Okay, let's look at square root functions, right? We know that we can rewrite square root functions as exponential functions, but with a the power that's a fractional power, right? So the general formula for any even roots is going to be x to the 1 over 2n. Alright? And this applies to any even functions, of exponential functions, alright? You're not going to have a continuous function, alright? Because it's going to go from 0 to infinity. But remember, you cannot plug in a negative number in here or else it would be imaginary. However, if you have a cube root, which is going to be x to the 1 over 2n plus 1, okay, that one is actually going to be a continuous function because you can actually have a negative number. So if you plug in a negative number here for x, you're actually going to get back a negative number. So here, for any even exponential, even square root or even roots, or it's going to be from 0, actually including 0, because we can still have 0. So we put a little bracket, comma, infinity. And here, it's just going to be all real numbers. Okay, so any cube root or any odd powered root, okay, is a continuous function. Alright, finally we have what we call, what is it called? Trig functions, right? So there are certain trig functions that have ratios. That's kind of a rational function. I didn't write it here, but tangent x is going to be sine over cosine, right? So you have to find where cosine is equal to 0. So what value, what radians, right, is going to be equal to 0. And the thing about these trig functions is that they're periodic. So that when you have the asymptotes, when you draw the graph, okay, it's not going to just be at one place, right? It's periodic. So you'll have asymptotes, you know, in various different places. So there's a certain formula. I can't remember what it is, but that's how these trig functions work. Cotangent is going to be cosine over sine x. So you have to find where sine x is 0, and we know generally where that is, right? That's going to be 0 and pi, right? So from 0 to pi, you're going to have an asymptote. All right, so you would say that you cannot have where your range or domain would be like from 0 to pi plus like every 2 pi, so it kind of cycles around. We have these inverse trig functions like secant and cosecant, right? Cotangent is an inverse function of tangent. Secant is 1 over cosine, so again, it's just going to be, where's cosine going to be 0? And that's where you're going to have your asymptotes. And the same thing with cosecant, which is 1 over sine. So generally, these are kind of like what you're going to encounter in algebra that have discontinuous functions. There's certain values of x that you can't plug in.